A quasar may release more visible energy than entire galaxies containing hundreds of billions of stars. Current observations suggest that some of these objects compress galactic-scale luminosity into what appears to be a single concentrated source, and the exact process behind that amplification remains uncertain. At the center of the system is a supermassive compact region, surrounded by an accretion structure pulling in enormous amounts of matter. As gas falls inward, gravitational energy is converted into radiation, causing the surrounding region to heat to extreme temperatures. Under normal expectations, the energy output of any localized object should remain constrained by the rate at which matter can physically accumulate and release energy. Yet some quasars appear to approach or temporarily exceed theoretical luminosity limits that standard accretion behavior struggles to explain cleanly. The first observable signal is not the object itself, but the sudden emergence of an extreme luminosity spike visible across intergalactic distances. Entire surrounding galactic structures may become visually overwhelmed by radiation originating from a region far smaller than the galaxy containing it. Current models suggest that the accretion process may not behave as a steady inflow. Instead, the system could operate through a feedback loop where incoming matter increases radiation pressure, while that radiation simultaneously alters the structure of the inflowing material itself. As radiation intensifies, parts of the surrounding accretion environment may become unstable. Some regions could be compressed inward, while others are pushed outward, creating a fluctuating transfer cycle rather than a stable energy release pattern. That instability creates a contradiction in the expected balance of the system. Strong radiation pressure should eventually reduce the rate of incoming matter, limiting further amplification, yet observations indicate that some quasars maintain extraordinary brightness for extended periods. One possibility is that the geometry of the accretion structure temporarily traps or redirects energy in ways that increase observed luminosity without requiring a proportional increase in total energy production. But this explanation depends heavily on viewing angle and internal structure that cannot be directly resolved. Another interpretation suggests that the feedback loop itself may repeatedly reorganize the inflowing matter, producing bursts of efficiency that standard steady-state models fail to capture. In this scenario, the system does not remain stable long enough for conventional equilibrium assumptions to apply. The observable pattern becomes increasingly difficult to reconcile with ordinary galactic behavior. A single active region begins dominating the radiative signature of an entire galaxy, making the surrounding stellar population appear almost secondary to the central source. Over time, the feedback cycle may intensify further as more material accumulates near the central region. Increased density produces stronger radiation, while stronger radiation alters the pathways through which additional matter can continue falling inward. That transformation creates a deeper uncertainty about what actually regulates the process. If the feedback loop naturally self-limits, the luminosity should eventually stabilize. Yet some observations imply episodes of persistent amplification that appear difficult to terminate cleanly. The system also changes observationally as surrounding gas becomes increasingly ionized by the emitted radiation. Light signatures from the environment begin reflecting not only the presence of extreme energy, but also large-scale structural disruption occurring around the quasar itself. At this stage, the anomaly is no longer simply high brightness. The system begins appearing disproportionately efficient at converting gravitational inflow into observable radiation, compared to what standard galactic energy transfer expectations predict. That efficiency creates another contrast between mechanism and observation. Most galaxies distribute energy generation across billions of stars, but quasars compress comparable or greater visible output into a highly localized energetic core. As the timeline progresses, the surrounding environment may become partially shaped by the radiation it produces. Outflows driven by extreme energy release can alter nearby matter distribution, potentially changing the future behavior of the accretion cycle itself. The feedback loop therefore stops behaving like a simple input-output process. Radiation modifies inflow, modified inflow changes radiation, and the evolving structure of the system begins influencing future stages of energy transfer in ways that remain difficult to model precisely. Some models indicate that the most luminous phases could represent temporary transitional states rather than permanent equilibrium conditions. If true, the brightest observed quasars may only exist during relatively unstable periods of galactic evolution, But that interpretation introduces another unresolved boundary. If these phases are short-lived, the number of extremely luminous quasars detected across cosmic distances may be larger than expected relative to the duration such states should survive. The observational difficulty becomes more severe because most of the relevant structure cannot be directly imaged at meaningful resolution. Astronomers infer the internal behavior of the system primarily through spectral changes, luminosity variation, and indirect signatures of surrounding matter motion. This creates a measurement gap between the observed energy output and the hidden physical structure responsible for producing it. The brightest part of the system remains partially concealed inside the very radiation field that reveals its existence. As the accretion environment evolves, small instabilities may scale into large radiative consequences. Minor shifts in inflowing matter distribution could potentially trigger major luminosity fluctuations, making long-term behavior increasingly difficult to predict. That sensitivity challenges the assumption that quasars can be modeled as stable large-scale engines operating under fixed conditions. Instead, the system may continuously reorganize itself through nonlinear feedback interactions that remain only partially understood. The deeper the luminosity spike becomes, the more the distinction between local and galactic scale behavior starts to blur observationally. A single energetic region begins shaping the visible identity of an entire galaxy across intergalactic distances. Current models can reproduce parts of this behavior, but no explanation fully resolves why some quasars appear capable of sustaining such extreme radiative dominance without destabilizing the mechanisms believed to power them. The transformation from ordinary galactic inflow into galaxy outshining luminosity remains physically plausible, yet the exact pathway controlling that amplification is still unclear. As luminosity continues increasing, the surrounding radiation field may begin influencing regions far beyond the immediate accretion structure. Energy released near the core can propagate outward through the galaxy, altering nearby gas behavior long before the central mechanism itself becomes fully observable. The quasar stops functioning like an isolated energetic source. It becomes a galactic-scale driver capable of reshaping the visible environment around it through sustained radiative transfer. This creates a growing observational asymmetry. The brighter the central region becomes, the harder it becomes to distinguish which effects originate from the core mechanism itself and which are secondary consequences produced by the radiation already escaping into surrounding space. Some measurements suggest that the emitted radiation may not spread evenly in all directions. If energy release becomes partially concentrated through narrow outflow regions, the apparent luminosity seen from specific observational angles could become significantly amplified, without requiring a uniform increase in total energy output. But that interpretation introduces a tightening constraint. Directional amplification may explain some extreme observations, yet several quasars still appear excessively luminous, even after accounting for likely orientation effects. The instability therefore appears deeper than simple geometric distortion. The feedback process itself may be increasing the efficiency of energy conversion in ways that remain difficult to reproduce consistently in current simulations. Small changes in inflowing matter density could trigger disproportionately large increases in radiative output. Once radiation pressure begins reorganizing nearby material, the system may enter temporary amplification phases, where local disturbances scale upward into galactic-level observational consequences. The visible result is abrupt intensity variation emerging from a region that cannot be directly resolved. Observers detect changing radiation patterns, but the underlying structural transitions driving those changes remain partially hidden inside the emission itself. As the feedback loop evolves, the surrounding accretion environment may no longer behave as a continuous flow. Portions of matter could fragment into unstable zones where radiation transfer, thermal pressure, and gravitational compression interact unevenly across different regions. That fragmentation complicates one of the central assumptions behind standard quasar modeling. Many equations rely on averaged large-scale stability, yet the actual system may be governed by rapidly shifting local instabilities that continuously alter the larger energy structure. The anomaly becomes harder to isolate because the observable signal is already a processed consequence of multiple hidden interactions. Radiation escaping the system may reflect not only the energy source itself, but also the constantly changing pathways through which that energy propagates outward. At extreme luminosity levels, even the surrounding galaxy may begin responding dynamically to the radiation field. Gas distribution near the central region can become displaced, compressed, or accelerated, feeding additional structural changes back into the accretion cycle over time. The system starts amplifying its own consequences. That escalation creates a deeper timeline uncertainty. If radiation-driven restructuring continues long enough, the feedback loop could gradually modify the future inflow conditions responsible for sustaining the quasar in the first place. Some models indicate that this self-modifying behavior may push the system toward unstable transition states rather than long-term equilibrium. But observational timelines are too short relative to galactic evolution to directly confirm how these transitions fully unfold. The brightest phases therefore appear as incomplete snapshots of a process unfolding across enormous timescales. What is observed may only represent brief, high amplification intervals within much larger cycles of structural transformation. Even so, the scale remains difficult to reconcile intuitively. A localized energetic region repeatedly produces observable consequences, extending across distances normally associated with entire galactic systems rather than compact central structures. This introduces an analytical tension inside the feedback interpretation itself. If the loop becomes too efficient, radiation pressure should eventually suppress additional inflow strongly enough to weaken the system. Yet the most luminous quasars appear capable of maintaining extreme output without obvious rapid collapse. Current models can partially stabilize this contradiction mathematically, but only under highly sensitive conditions. Small parameter changes often produce dramatically different long-term behaviors, suggesting that the system may operate near unstable physical boundaries rather than inside stable regimes. The observable radiation, therefore, may not represent a steady state at all. It could instead reflect a continuously adjusting process where the mechanism sustaining the luminosity is simultaneously pushing the system toward conditions that threaten to destabilize it. Some quasars also display fluctuations that appear inconsistent with the enormous scale implied by their brightness. Variability can emerge faster than expected for structures operating across such large energetic regions, implying that hidden local interactions may dominate behavior more strongly than the visible scale initially suggests. That mismatch between observed variability and apparent size sharpens the unresolved dependency inside the system. The quasar appears galactic in consequence, yet parts of its behavior may still be controlled by compact processes unfolding near the central feedback region. The deeper the luminosity spike becomes, the more the distinction between local mechanism and galactic scale outcome begins collapsing observationally. Current observations reveal the consequences of the transformation clearly, but the exact chain controlling how accretion feedback reaches such extreme amplification remains uncertain. The original expectation was relatively simple. A quasar was understood as an extreme but ultimately scalable consequence of gravitational accretion, where incoming matter produced radiation according to physical limits that could in principle be modeled and stabilized. But the brightest observed systems no longer fit cleanly inside that interpretation. The feedback process appears capable of reorganizing the surrounding environment, amplifying local interactions into galaxy-scale radiative dominance, while remaining only partially observable from the outside. What changed was not the existence of quasars themselves, but the scale of what their behavior now implies. The system no longer appears to function as a compact energy source operating inside a galaxy. In some cases, the surrounding galaxy begins behaving more like a secondary structure, shaped by the radiation emerging from the central feedback loop. Current models can describe portions of this transformation, but they still struggle to explain how the amplification process remains sustained without fully destabilizing the mechanism producing it. The visible luminosity is measurable. The internal pathway controlling that luminosity is not. A single energetic region appearing brighter than entire galaxies is no longer treated as an observational mistake. It is treated as a real physical outcome emerging from a system whose governing limits remain uncertain.